Hello. In this topic, we look at two more distributions, and then we're going to be comparing it to the third one and contrasting. So in a prior topic, we looked at what's the binomial distribution, situations where only two things can happen, successes, failures, each event is independent of another. So that's one type of distribution. And then today we're going to look at what's known as a geometric and a Poisson distribution. And then we're going to just look at a variety of different scenarios and compare and contrast the two. So the very first one, lead in, introduction situation, it says LeBron James has a career free throw percentage of 75%. What is the probability that the first free throw shot he makes in a game occurs on his fourth attempt? Note, in order for this to happen, what has to happen with the first three attempts? So give yourself maybe a second to think about it if you want to try. Otherwise, I'm going to talk about it right now. The probability that his first make is on his fourth attempt means he has to miss each of his first three attempts. The probability he makes is 75%, so the probability he misses is 25%. So he needs to miss, and he needs to miss, and then he needs to make. It says each of these are connected by ands, and they're independent of one another. I would end up with 0.25 to the third power times 0.75. Grab a calculator and run that. The likelihood that that occurs is about 0.012, about 1.2% likelihood that that is going to occur, that his first make is going to be on his fourth attempt. This type of situation has a name. It is known as a geometric distribution. Many actions in life are repeated until a success occurs. For instance, you might attempt to start a machine several times before you are successful. And then once you're successful, there's no point in continuing, so we stop. These types of situations are called a geometric distribution. Geometric distributions are for a discrete probability distribution. You have to be able to count the individual trials. They have to satisfy the following conditions. A trial is repeated until a success occurs. The repeated trials are independent of each other. The outcome of one is not going to affect the other. The probability of success, P, is constant for each trial. That has to deal with the independence. The random variable X represents the number of trials in which the first success occurs. Then the probability that the first success occurs on trial X is going to be Q to the power of X minus 1. These are all the prior failures, times P, the first success, where Q is equal to how many failures we had occurring. So for example, in our prior situation with LeBron James, 25% failure, we want it to be on his fourth attempt, so 4 minus 1 is 3, times the probability of 0.75. If you go back and look at the warm-up, that's exactly what we had. We had 0.25 to the third power times 0.75. So it works. Our natural intuition kind of guided us to this result. We call this a geometric distribution. To find the probability that the first successful event occurs on the xth event with probability P, this is built into the calculator, the geometric distribution calculation. You simply go to second, distribution, then you select geometric PDF. You have to first list the probability of success on any given trial, and X is the number of the trial on which you want the first success. But honestly, these are just as easy to do without the pre-programmed formula, as we'll see. A couple examples. Let's say an auto parts seller estimates 1% of all parts sold are defective. What's the probability that the first defective part he sells that day occurs on his 10th sold part? As an example, I'll use the calculator, and then I'll show how to do this kind of just by hand, and then we'll use the calculator going forward. But his 10th sold part. If I were going to use the calculator, I would first need to define what the probability of success is. The probability of success is 0.01. And we want it to occur on the 10th trial. So if I grab a calculator, I'm going to go to second, let's get out of here, second distribution. I want to choose geometric PDF, which is option E. Probability of success is 0.1, which is finding a defective part, which is kind of a weird way to find success, but that's what it is in this case. You should probably list that. We should say success entails finding defective part. 10% likelihood, we want it to be, what do we say, on the 10th sold part, or sorry, not, no, I wanted a 1%, so 0.01 on the 10th trial, and I run it, and the likelihood of that occurring is 0.009. So geomet PDF 0.01 comma 10 equals 0.009. How else could I do this? Well, if the first success was on the 10th attempt, he had 9 failures beforehand, which is 99%. So 0.99 to the 9th, and then I need a final success. So I grab a calculator, type in 0.99 to the 9th times finally a success of 0.01. And if I run that, you get the exact same number. So you can either do it by hand or using the built-in program in the calculator. Second situation, what's the likelihood that the first effective party sells is either on his first, his second, or his third? And I can use geometric CDF because that'll do everything less than that. So this would be the case of doing geometric PDF for the first one would be 0.01 comma 1, or the second would be geomet PDF 1% success on the second one, plus, because it's an or, geometric PDF 0.01 on the third. This is simply equal to, I can just run one calculation, geomet PDF, not PDF, sorry, CDF, it's combined continuous distribution, really. Geomet CDF does anything less than that, or equal to that. So 0.01 on the third. Grab my calculator, go to second distribution, and I'm going to choose CDF. What this means is I want for a 1% success rate, if I put in 3, this will calculate the probability of the first success occurring on the third, the second, or the first. So it does 3 or less. I get 0.029, so about 0.03. Just a shorthand way of doing 3 or less. Last one, what's the likelihood it occurs on none of his first 10 parts? Well, technically, this really isn't a geometric distribution, so we haven't even had a success yet. If he had 10 straight failures, how would we calculate that? Well, this would just be 0.99 to the 10th. If you grab a calculator and type in 0.99 to the 10th, the likelihood he fails on all 10 events, which means his first 10 parts are all good parts, that is a 0.904. 90% chance that the first 10 parts he sells are all going to be good. That is a geometric distribution. The next one, and the last one, is called a Poisson. So in the prior lesson, we studied what was known as the binomial distribution, which allowed us to find the probability of a set number of successes in a given number of trials. That's what a binomial one is. However, if instead we wanted to know the probability of a set number of successes in a given unit of time, area, or volume, it turns out all of these things naturally form towards what's known as the Poisson distribution. For example, if I wanted to find the probability that an employee will take 15 sick days within 1 year. 1 year is a unit of time, so I'd use a Poisson distribution. To see where a Poisson distribution comes from, you'd have to take a higher end calculus-based statistics course, so the result will just be given to us. In order to apply a Poisson distribution, again, we have to be counting a discrete number of things, can't have decimal portions of things. The following conditions need to be true. The experiment consists of counting the number of times an event X occurs in a given interval, how many successes. This interval can be for time, area, or volume. If it's a number of trials, it'll be a binomial, but if it's time, area, or volume, it will follow a Poisson distribution. The probability of the event occurs is the same for each interval, consistent. The number of occurrences in one interval is independent of the number of occurrences in the other interval. The probability of exactly X successes or occurrences in this interval is given by the following probability. It's equal to mu stands for the mean, so the average number of successes we usually get, to the power of X times E. E is the irrational number 2.71818 ... to the power of negative mu, negative the average, all over x factorial. You can see how this is kind of an interesting distribution you absolutely would not think of on your own. So we're just going to be using the result. Situations where the Poisson is useful would be number of phone calls received by a call center per hour, that's a unit of time. Number of decay events per second from a radioactive source, this again is per unit of time. Number of meteorites greater than 1 meter in diameter that strike the Earth in a year, unit of time. Number of patients arriving in an emergency room between 10 and 11 p.m., a unit of time. Number of deadly bacteria in a lake in a year. So this is in a unit of volume in a lake and time in a year. That's why these are all Poisson distributions. Example of using a Poisson. We'll see in just a second after I just mentioned to you that the calculator has this built in as well. So you don't have to type in this formula. Actually, you don't have to use this formula right here because the calculator has it built in for you in the Poisson distribution. You simply go to second, distribution, Poisson PDF. PDF because we would be doing a specific number of trials. Be aware if you're using a TI-84, they actually use lambda L instead of mu. So here we go. The mean number of accidents per month at a certain intersection is on average 3. What is the likelihood then that on any given month we're going to have 4 accidents occurring at that intersection? Well, the mean, mu, is 3. We want to know what's the likelihood we get 4 successes though. So I'd use a Poisson distribution. I can either type it into the equation, so in this case I would use mu as 3 and I put in 4 for x and I run the equation. It looks like about 17%, 16.8, or I grab my calculator, I go second, distribution. The reason that this is a Poisson, I should mention, is because we're doing this over a unit of time. Time would be occur at this intersection in a month, per month. So I go to Poisson PDF, options right there. Lambda, we average 3 accidents per month. What's the likelihood we actually get 4? I ask it to run it, and there's my 0.168. The exact same thing I did if I'd used the equation. So a 16.8% chance that I would have 4 accidents at that intersection. I'm going to give you a chance to try, just one today on your own. State whether the following is a geometric or a Poisson distribution, and then find the corresponding probability. A newspaper finds that the average number of errors per page is 4. What's the likelihood that the number of errors found on any given page is actually 2? So pause the video now, come back and check once you've had a chance to try. This would be a Poisson. First off, it's not geometric because in order for it to be a geometric, they have to say what's the probability that the first success occurs on this trial. We're not even talking about any like first successes. We're saying on average there's 4 errors per page, so that's a unit of area. What's the likelihood on any page we have exactly 2? So this is a Poisson. It's a Poisson where my average mu is equal to 4 and my number of successes x is equal to 2. So I run Poisson PDF 4, 2, and I get about a 15%, 14.7% chance of that actually occurring. And those are all the distributions that we look at in this section. The following summary of the 3 types of discrete probability distributions, a binomial, a geometric, and a Poisson, are given on page 219. We're going to practice identifying each of the following situations, but if you want to look through on page 219, they describe when each of these is going to occur, what the notation is for the variables in those formulas, and then they provide the formulas if needed. So you can maybe consult that if you'd like. We're going to look through some examples. So for each, our goal is to state the distribution, the corresponding probability, and whether it is unusual. An unusual event is anything that occurs with a probability of less than 5%. We're going to call unusual. And that has to deal with more than 2 standard deviations away using the empirical rule. Situation number 1. The probability that you will make a sale on any given phone call is 19%. What's the likelihood that your first sale of the day is on the 5th call? Well, this is going to be a geometric. It's a geometric because we're talking about what's the likelihood your first success occurs on some xth trial, in this case the 5th trial. The corresponding probability, I'm going to use geometric PDF. Things we need to know are the probability is 19%, and we want our first success to be on the 5th trial. Grab my calculator, go to my distributions, choose my geometric PDF, probability of success is 19%, so 0.19. What's the likelihood my first success is on the 5th trial? Ask it to calculate it, and it's about an 8%, 0.082. Is this unusual? No. 0.082 is greater than 5%. So it occurs 8% of the time, which isn't highly unusual. Next, 2 examples. Second one, 80% of adults favor using renewable energy. You randomly select 8 adults. Find the probability that 3 or less say they favor renewable energy. This is going to be a binomial. We know the probability of success is 80% for anyone. We randomly have a fixed number of trials. So we have 8 adults, and we want to know the likelihood that we get 3 or less that favor renewable energy. Since this is a fixed number of trials, this is going to be a binomial distribution. Success or failures. Only 2 options, that's why it's binomial. Probability. I'm going to be using binom, and because it says 3 or less, we're going to use CDF. So I don't have to do 3 and then 2 and then 1 and add them all together. In order to use binom CDF, I believe the first thing you need to tell it, well, let's go. Let's do it. I'll write them down afterwards. So second distribution, it looks like it prompts me first for trials, then probability, then how many successes I want. So trials in this case is 8 trials. Probability of success is 80%. And I want 3 or less. So I should put this is going to be a CDF because of 3 or less. And then I ask it to run it. So 8.8, 3 or less successes. Ask it to run it. It's about a 1% chance. 0.01. Is this unusual? Yes. This is unusual since 0.01 is less than 5%. We would say this event occurring is unusual. Why is it unusual? Well, because 80% of favor it. The likelihood we randomly sample 8 and get 3 or less is probably not going to happen because 80% of each individuals are going to be in favor. It'd be pretty rare that we find 3 or less that are going to say yes or say the opposite in a small sample of 8. Last scenario. In Savannah, Georgia, the average number of days in July with rain is 13. Find the probability that next July, the number of days with rain in Savannah is more than 16. Well, this has to be a Poisson. It's the only one we haven't looked at so far. And the reason why is because it is asking for a probability over a fixed time period. So a month. The probability would be, this is asking for what's the probability. Well, let's actually kind of hide this and do it a little step by step. Probability, the number of days with rain is more than 16. If I want the probability of getting more than 16 days, I could find the probability of getting 16 or less and then subtract that from 100%, because I can do Poisson CDF to get 16 or less. Into my calculator then, I would type in 1 minus Poisson CDF. The average is 13. What's the likelihood I get 16 or less days of rain? Well, that's 83.5%, which means the complement would be 1 minus that. 1 minus it is going to be, what is that, 16.5? Is this unusual? No, not even close. 16.5% is way greater than 5%, so this is not unusual. And that's it for the topic. Thank you very much. Have a good day.